This is for showing resonance, and I'm going to start out with wave on a string, and I'm going to take oscillate, and depending on the damping, I get a wave in here, and it kind of just flattens out because it gets less and less because of the damping. I'm going to pause this here for just a moment. If this one here would stop wiggling, and we already have a wave here that could be reflected and reflected here again, then we would just have a wave here that is being reflected over and over again. But an interesting thing is going to happen if we decrease the damping and have this one here vibrating up and down, because now we have a wave that is then being reflected here, and on top of it, and then again reflected, and then on top of it there's a new more energy coming in due to the vibrating oscillator here, so it puts more and more energy into the system, and this is what you see when there is no damping, and there's just a catastrophe happen here. To continue with resonance, I'm going to choose this one here. And I have this applet here on resonance, and I have a frequency of 1.00 Hertz, and my driver is at a frequency of 1.00 Hertz. So the spring itself likes to vibrate at 1 Hertz, and then it gets a push every 1 second just at the right time. And basically the same thing is happening as you saw. So it gets larger and larger, and then it depends on the damping constant. If I increase the damping, it's going to be okay. And so, for example, I have good shock absorbers in my car. This here might be the road that the car is driving over, and so it's a bumpy road that gives it this push here, and then the shock absorber is dampening pretty good. This here would be part of the car that the shock absorber is connected to, and sure, yes, the car vibrates, but not too bad. What about if there are bad shock absorbers like this one here? And with time it just gets worse and worse. The driver, that is this driver here, puts the energy in at just the right moment to matching the spring's natural frequency, and it just makes it vibrate more and more. I don't think I can. No, I can't get any less than this here. So yeah, it's again another catastrophe that will happen. Here I'm going to show several resonators. So I'm going to increase the number here to 4, and then when I turn this one on, this one is right now set at 1.00 Hertz, where I showed that number 1 here is swinging the most because it matches its natural frequency. Again, if I move the damping constant down, then this will end in catastrophe. What about the second one, where you can see over here that the numbers are different? So I would change the driving frequency here. We can see number 2 is starting to take off. Okay, a little more. Okay, pretty bad here. And then here's actually getting less, and number 3 actually starts to take over. Instead of just guessing, I'm going to calculate it, and I'm going to use both the number 2 resonator, and from its mass, 1.6887 kilograms, and its spring constant 150 newton meters, I will determine what its frequency should be, And then for number 1, it's going to be 2.533 kilograms and 100 Newton meters, and I'll show that that matches the 1.00 hertz. So natural frequency of a spring and that actually gets me back to a previous chapter on simple harmonic motion, where I look up that the angular velocity omega equals the square root of k over m. Both of these are given. And the angular velocity is 2 pi, that's supposed to be pi, 2 pi times the frequency, where I want to determine the frequency. So it's going to be F equals square root of k over m divided by 2 pi. And for resonator 1, that would be 1 over 2 pi times its spring constant was rated as 100 newtons per meter, and its mass as 2.533 kilograms. Square root of that. When you do the unit analysis here, the kilograms divide out with the kilograms that is inside the newtons, and then the meters divides also out because there's a meter inside the newton, because newton has kilograms meters per second squared. Take the square root of the remaining per second squared, you come up with 1 over second, which is hertz. That was pretty quick here for the unit analysis. I'm going to shift this over a little bit so it's in the picture. And so now I'm going to do the calculation, and when I do that, 2 pi times the square root of 100, 2 pi to negative 1, that is 100, divided by 2.553, and I come up with 0.996 hertz, or around it 1.00 hertz, which is of course what we saw. And then for the resonator number 2, starts out the same, 1 over 2 pi, and then that one was rated at 150 Newton meters divided by 1.688 kilograms. They wanted to really give that exactly to us. And when I do that, unit of course is hertz. And when I do that, I'm going to come up with 150 and 1.68887, 1.49999 hertz, so around it 1.50 hertz. So when I move this one back here, I'm going to go down here to 1.50 hertz. I don't know if I can get this exactly. I guess I can type it in. And this is where it vibrates the most, especially when I turn the damping constant down. Yeah, number 2 is going to go up to the catastrophe. Actually, there we go. Somehow I typed it in, but I didn't accept it. So there we go. And if I move it a little bit away from it to like 1.6, even though the damping is small, it actually calms down. It's going to do it again where we'll see this beat that we saw in an earlier recording. If I move this one up here, oh, by the way, and I do realize that I have given away here already the natural frequency of it, but I wanted to show how it can be calculated to see what would lead to that catastrophe. So if I turn this one here up for the driver frequency, then we can see that number 3 is taking over. If I'm able to click on this one here, we can see its specifications, and the resonant frequency should be at 2.0 hertz, and then if we go beyond that, eventually it's going to calm down and number 4 will take over. Okay, it's pretty wild here. That was it on the lectures for sound and waves.